Hi, thanks for tuning into Singularity Prosperity. This video is the second in a multi-part series discussing computing. In this video, we'll be discussing modern computing, more specifically Moore's Law with the exponential growth of technology due to our ability to pack more and more transistors into integrated circuits, and the potential death of Moore's Law. In the previous video, we discussed the evolution of the field of computing, from the pre-computer era to vacuum tubes, transistors, and finally the integrated circuit. I highly recommend you check it out for some more background context into computing. One of the largest breakthroughs in electronics and computing was the integrated circuit, a way to put many transistors into a single chip instead of individually wiring them together. After Gordon Moore, one of the founders of Intel, saw this doubling of transistors on integrated circuits, he extrapolated the data and made one of the greatest predictions in human history. The number of transistors and resistors on a chip would double every 24 months. In other words, computing power would double every 24 months at low cost. Integrated circuits are used in practically every device that requires a digital logic operation to be done. These operations can consist of converting analog signals to digital, amplifiers, computation-oriented, the list can go on and on. As our world becomes more digitized, the amount of integrated circuits will only continue to increase. In fact, every year since the birth of the IC in 1958, more and more have been produced year in and year out, with for the first time ever in 2018, more than 1 trillion to be produced in just that year alone. The most astonishing part about this fact is that this number is only set to grow, as sensors and computers become ever more ubiquitous and affordable. Looking at just one field in the broad scope of technology, the Internet of Things, connected devices are expected to nearly double from this year to 2020, reaching over 50 billion, with each one of those devices having tens, hundreds, or even more ICs within them. Almost everything is on its way or has an IC in it, from airplanes, cars, speakers, Blu-ray players, toys, door locks, lights, and countless other technologies. The real power of ICs, however, and what has really shaped our world and fueled the growth of Moore's Law, is the use of ICs for computing. When we think of computers, the first component that often comes to mind is a microprocessor, a specialized integrated circuit that is made for computing. Microprocessors used to be just one IC, but as computers evolved and more complexity in design was needed, a central processing unit emerged. A CPU, simply put, is a part of the computer that executes instructions. It can be implemented using a single IC, multiple ICs, individually wired transistors, or a room full of vacuum tubes and relays. A microprocessor is just a single chip implementation of the CPU, which is why the terms are often used synonymously. Other examples of where integrated circuits in modern computers are used is the RAM, DRAM, hard drives, solid-state drives, GPUs, the motherboard, which is essentially many ICs with many functions, and more. Essentially, there are tens of hundreds in typical computers, each with a specific task. As the number of transistors on integrated circuits has increased, has led to the ability for the production of components with more storage, speed, memory, etc. than ever before at increasingly affordable prices. In 1971, the first commercial microprocessor, the Intel 4004, had a transistor count of 2300. 8 years later, in 1979, the Intel 8088 had 29,000. 10 years later, the Intel 80486 had nearly 1.2 million. Then in 1999, the Pentium 3 had 9.5 million. And following that in 2000, the Pentium 4 had 42 million. Since the 2000s, the transistors on chips have been increasing at an increasingly fast rate. While this applies to microprocessors, similar trends have been followed in all integrated circuit applications. For example, as seen in the price of memory and storage over the years per gigabyte as the number of transistors has increased. The majority of people nowadays have a computer, whether it be a desktop, laptop, or more commonly, a smartphone. While the latest commercial desktop and laptop processors are using 14nm transistor sizes, as of this year the mobile industry has pushed forward with 10 nanometers. The Samsung S8 with its Exynos 8895, Qualcomm's Snapdragon 835, and Apple's iPhone X with its A11 Bionic chip all feature a 10nm transistor process. To put that number in perspective, 10 nanometers is 1 billionth of a meter, 0.000000001 meters. 20 silicon atoms wide. You can fit about 10,000 along the width of an average human hair. When holding your new phone, you're essentially holding 3 to 4 billion transistors. As seen here, transistor sizes have been decreasing exceedingly fast since 1971, but since the 14 to 16 nanometer range, things have slowed down quite a bit. One of the primary reasons this was due to was quantum effects. One of these effects is quantum tunneling. This caused because the distance between the source and drain of the transistor is so small that electrons jump across the barrier. So instead of staying in their intended logic gate, the electrons end up continuously flowing from one gate to the next, essentially making it impossible for the transistor to have an off state.
Here is a conventional planar CMOS transistor. On top of a silicon substrate are two electrical terminals, the source and the drain, separated by an electrically controlled gate. When voltage is applied to the gate, a conductive channel is formed and electrons flow from the source to the drain. When voltage is removed, the current should completely cease. However, in modern transistors, substantial leakage flows even when the gate is turned off. Unfortunately, this leakage current increases with every generation of transistor and represents a growing proportion of power consumption.
To solve this, a radical redesign of the transistor has taken the industry by storm, the FinFET. The fin-shaped field effect transistor essentially takes a typical 2D planar transistor and reorients the gate vertically to make it 3D. This allows more gate control since now the gate of the transistor covers the top and sides. This therefore reduces the leakage induced by quantum tunneling. Each FinFET has 3 fins, with the fins being the source and drain of the transistor going through the gate. The FinFET also allows for less heat generation and power consumption since now one gate can essentially control 3 nodes, which correlates to longer battery lifespans. FinFETs allow the scaling of transistors from 16 nanometers to 10 nanometers, as exemplified by the mobile processors mentioned earlier. And now other major semiconductor manufacturers such as Intel are releasing their 10 nanometer desktop and laptop lines in 2018, with Canon and Ice Lake. As a side note, Intel has been using FinFETs since their 22 nanometer Ivy Bridge architecture, referring to them as tri-gate transistors. FinFETs should allow scaling down to 7 nanometers with minimal leakage, with IBM successfully demonstrating a 7 nanometer node in 2015 and release expected by the 2019 to 2020 range. Unfortunately, when scaling lower than 7 nanometers, quantum tunneling once again rears its head. The further miniaturization of transistors will open up the Internet of Things for everybody, with the ability to embed sensors into nearly anything. What's more exciting to me personally is the applications of this miniaturization on microcontrollers like the Raspberry Pi, which is now more powerful than some early to mid-2000 level computers. All of the technological leaps and bounds due to the miniaturization of the transistor have been amazing, but harbor one question: when will the shrinking of transistors stop and Moore's Law end? At its current definition, the acceleration of Moore's Law cannot continue forever. Currently, Moore's Law is a physical law. It is linked to the size of a silicon atom. Therefore, we will hit a minimum value for the size of a transistor. As explained previously, FinFETs have allowed scaling of transistors down to 7 nanometers, with 5 nanometers still being a theoretical possibility, but that may not work due to electron leakage induced by quantum tunneling. Recently, as of June 2017, IBM announced they had scaled down the transistor to 5 nanometers by reorienting the transistor once again, and were able to fit 30 billion transistors on a chip the size of a fingernail, from the 2D planar to 3D FinFET, and now to the GAFETs, the gate all-around field effect transistor, which is sort of a 2D 3D mix and relies heavily on FinFET design methodologies. The GAFET essentially adds another transistor compared to FinFETs. Instead of the fin of the source and drain being aligned vertically, GAFETs align them horizontally using silicon nanosheets, as seen in this photo. Due to these added transistors, devices will become more power and heat efficient once again, up to 40% faster and 75% more efficient compared to 10 nanometer processors that are just coming to market today.
Using silicon nanosheets, we enable 5 nanometer technology. To do this, we developed an entirely new architecture. Today's chips use what is known as a FinFET architecture, and we even use it in our state-of-the-art 7 nanometer chip.
But go to beyond 7 nanometers and build new 5 nanometer technology. We use stack of silicon nanosheets.
Here we can see the difference between today's FinFET architecture and the stacked nanosheets. Instead of 3 fins side by side, in which the current flows along the side of the fin, the silicon nanosheets are layered on top of one another, and the current flows along the direction of the sheet.
It's clear today 5 nanometer chips are possible, and it's going to happen.
The GAFET is expected to start rolling out to market around 2021 to 2023, and this technology is also theorized to allow scaling down to 3 nanometers, which is now in its research phase and may come to market around the 2024 to 2026 range. At 1 nanometer, we reach the smallest a transistor can go if we rely on silicon. At 1 nanometer, the source and drain are 2 silicon atoms across. It is unknown if we could reach this milestone at a commercial level, but some tests do show promise through the use of carbon nanotubes and other design methodologies. Moore's Law based on the miniaturization of the silicon transistor will die around the mid to late 2020s. Now all those people, articles, videos, even this video use Moore's Law being dead as a provocative title. Beyond the miniaturization of the transistor, there are various other aspects of computing to perfect before Moore's Law even comes close to ending. In fact, it may never end until we reach Planck level technology at 10 to the negative 35 meters in size. So what we will see in the next few years is an uncoupling of Moore's law from transistor density and more towards raw computing performance through multiple design methodologies. Looking at the progression of Moore's law in terms of computing performance over the past 120 years from Babbage's analytical engine, we can see that the last 7 data points are given by GPU performance, not CPU, with some of NVIDIA's latest cards having over 8 billion transistors, with the Titan X, their latest card, having 12 billion, and still using a 16nm FinFET architecture. In the next video in this computing series, we'll expand further on GPUs as computing alternatives, as well as other ways to maximize classical computing architecture, from new materials, FPGAs, additional cores, and more. In videos afterwards, we'll discuss various new branches of computing that are currently being developed, such as parallel computing like bio and quantum computers, optical computing, and neuromorphic computing. At this point, the video has come to a conclusion. I'd like to thank you for taking the time to watch it. If you enjoyed it, please leave a thumbs up, and if you want me to elaborate on any of the topics discussed or have any topic suggestions, please leave them in the comments below. Consider subscribing to my channel for more content, follow my Medium publication for accompanying blogs, and like my Facebook page for more bite-sized chunks of content. This has been Encore, you've been watching Singularity Prosperity, and I'll see you again soon.